Welcome back to the MCP Fundamentals series. This is episode 2. In the last episode, we talked about the N times M problem, how connecting AI models to tools was a total mess before MCP. Every model needed a custom integration for every tool. 5 models, 10 tools. That's 50 separate integrations to build and maintain. MCP solved that with a protocol. You can find that video in I button. But here's the thing, knowing why MCP exists is only half the story. Today we go deeper. We're going to answer the question every developer asks after the first episode. Okay, but how does it actually work? And that's exactly what we're covering today. The three-layer architecture at the heart of MCP, the host, the client, and the server, how they talk to each other, what protocol they use, and what a real end-to-end flow looks like. By the end of this video, you'll be able to look at any MCP integration, Claude Desktop, Cursor, VS Code, whatever, and understand exactly what's happening under the hood. Let's get into it. Before we jump into today's content, let me do a really quick recap. You can skip this part if you want or switch to 2 times playback speed. In last episode, we established the N times M problem. If you have 5 AI models and 10 external tools, you need 50 separate custom integrations. Every time a tool updates its API, integrations break. Every time a new model ships, you're rebuilding connectors from scratch. It was unsustainable. MCP answer was a protocol. Instead of every model talking directly to every tool in its own custom way, you have one standard protocol. Models speak MCP, tools speak MCP, and suddenly any model can use any tool without anyone writing custom glue code. We saw the hub and spoke architecture, N plus M connections instead of N times M. But what we didn't cover is what actually happens inside that protocol. When Claude Desktop calls a GitHub tool through MCP, what's the host doing? What's the client? What's the server? What format do they send messages in? That's what today is about. Let's go. MCP's architecture has exactly 3 layers, and understanding each one is the foundation of everything else in this series. At the top, you have the host. The host is the application the user actually interacts with. Claude Desktop is a host, Cursor is a host, VS Code with Copilot is a host. The host is responsible for managing the overall AI experience. It holds the conversation, it manages context, and it decides which MCP servers to connect to. In the middle, the client. Now, this is the one developers sometimes get confused about. The client lives inside the host. It's not a separate application. Think of it as the protocol engine that the host uses to talk to MCP servers. When Claude Desktop wants to call a GitHub tool, it's the client that handles all the MCP protocol details. At the bottom, the server. This is where capabilities live. A GitHub MCP server exposes tools like create issue or list pull requests. A Postgres MCP server exposes tools for querying your database. Servers are what you build when you want to give AI agents access to a new system. And here's the key thing to remember. One host can run multiple clients at the same time. So Claude Desktop can be connected to a GitHub server and a Slack server and a Postgres server all simultaneously. That 3-layer picture, host, client, server, is your mental model for everything that follows. Let's zoom in on the first layer, the host. The host is the application you're actually sitting in front of. When you open Claude Desktop and start a conversation, you're talking to a host. When you use Cursor to write code and ask the AI to pull a GitHub issue, you're in a host. The host is your interface to the AI. But the host does more than just show you a chat window. It's responsible for 3 critical things. First, it manages the LLM and the conversation context. All those messages, the system prompt, the conversation history. That lives in the host. Second, and this is important, the host is what spawns the MCP clients. When Claude Desktop wants to connect to a GitHub MCP server, it creates a client inside itself to handle that connection. The host is in control of which connections get made and when. Third, security. The host enforces user permissions. It decides what tools the user is allowed to invoke, and it can prompt the user for approval when a tool wants to do something significant. Look at the real-world examples on the right. Claude Desktop, Cursor, VS Code with Copilot, Z. These are all hosts. And the green card at the bottom right is important. Your app. You can build a host too. If you're building an AI-powered developer tool or agent, your application becomes the host. The host is the entry point to the entire MCP ecosystem. Now the client. This is the layer that confuses most developers when they first encounter MCP. So let me be really clear about it. The client is not an application you install or run separately. It is a component that lives inside the host. When Claude Desktop wants to talk to a GitHub MCP server, it creates a client internally to manage that specific connection. Think of the client as the protocol engine. Its entire job is to speak MCP fluently on behalf of the host. It handles all the low-level protocol details, the message format, the handshake, the capability discovery, the error handling. And here's the critical relationship to understand. It's one-to-one. One client connects to exactly one server. Always. But look at the diagram on the right. Claude Desktop, the host, can contain multiple clients simultaneously. Client A connected to GitHub, client B connected to Postgres, both running at the same time independently. So, from the user's perspective, Claude Desktop looks like one application connected to everything. But under the hood, there are multiple clients, each managing its own dedicated server connection. This design is intentional. By isolating each server connection into its own client, MCP ensures that problems with one server don't cascade and break everything else. Failure isolation is built into the architecture. The MCP server is where the actual capabilities live. It's what you build when you want to give AI agents access to a new system or dataset. Every MCP server exposes three types of things, three primitives, and understanding these three is fundamental. First, tools. Tools are actions, things the AI can actually do. Create a GitHub issue, query a database, send a Slack message. Tools are the most commonly used primitive, and they're what people typically think of when they think about MCP. When the AI wants to take action in the real world, it calls a tool. Second, resources. Resources are data the AI can read. A file, a database schema, an API response. Resources are more like, give me access to this thing, rather than do this thing. Think of resources as the AI's read-only window into your system. Third, prompts. Prompts are pre-built prompt templates that the server exposes to the host. So a GitHub server might expose a code review prompt template or a bug report wizard. These make it easy to build consistent, well-structured AI interactions for specific workflows. Every MCP server declares its capabilities through these three primitives when a client connects. The client discovers them and the host can use them. So we have three layers: host, client, server. But how do they actually communicate? What format do the messages take? The answer is JSON-RPC2. That's the wire protocol that MCP is built on. Every message that flows between a client and a server is a JSON object following the JSON-RPC2 standard. Look at the request format on the left. Every request has the same basic shape. JSON RPC tells you which version of the protocol you're using. Always 2.0. Method is what you're asking for. Things like tools/list to discover available tools, or tools/call to invoke one. ID is a correlation identifier so you can match responses to requests. And params carries any arguments the method needs. Now look at the message flow on the right. This is the standard dance that happens every time a client connects to a new server. First, the client sends a tools or list request. Hey, what tools do you have? The server responds with a list of every tool it exposes, including the name, description, and input schema for each one. Then when the AI wants to actually use a tool, the client sends a tools or call request. Run this tool with these arguments. The server executes it and sends back the result. That's it. That's the protocol. Clean, simple, stateless JSON messages, no magic, no proprietary binary format, just structured JSON that any developer can read and debug. We've covered the message format, JSON RPC 2.0, but here's a question. How do those JSON messages actually travel from the client to the server? Over what channel? That's the transport layer. and MCP gives you options. The first option is stdio, standard input output. This is the simplest transport and the one most people start with. The client launches the server as a child process and communicates with it through its standard input and standard input streams. No network involved at all. This is what Claude Desktop uses for local MCP servers. You configure a server in Claude Desktop's config file, it spawns the process, and messages flow over stdio, fast, simple, zero network overhead. The second option is HTTP with server sent events. This is for remote servers. The client sends requests over standard HTTP post requests, and the server streams responses back using server sent events. This is what you use when your MCP server is deployed in the cloud, on Vercel, on AWS Lambda, wherever. HTTP transport makes your server accessible from anywhere on the network. The third option is custom. MCP defines a transport interface, an abstract contract for how messages should flow. You can implement that interface yourself using WebSockets, gRPC, or any other protocol that makes sense for your environment. The practical takeaway: if you're building a local tool for developer use, start with standard input. If you're deploying a production MCP server in the cloud, use HTTP plus SSE. Custom is for specialized cases. All right, let's put it all together. This is the moment where everything clicks. Here's the full end-to-end flow, and I'm going to walk you through a concrete example at the same time. You, the user, type into Claude Desktop. List all open pull requests in my repo. Step 1. The host receives your message. It passes it to the LLM along with all the context, including a list of what tools are available from connected MCP servers. Step 2. The LLM, the model itself, reads your message and the available tools and decides I should call the list pull request tool on the GitHub MCP server. It returns a tool call instruction to the host. Step 3. The host delegates this to the client that's connected to the GitHub server. The client formats a proper JSON-RPC request, tool/call with the tool name and arguments, and sends it to the server. Step 4. The server receives the request, validates it, calls the actual GitHub API, and returns the list of open pull requests as structured JSON back to the client. Step 5. The result travels back up, client to host, host to LLM. The LLM takes that raw JSON data and formats it into a natural language response that you can actually read. That full round trip from your question to the answer might take a second or two, but now you know exactly what happened at every step. This is how AI agents talk to the world. Let's make this concrete with the most common real-world example: Claude Desktop connecting to the GitHub MCP server. Look at the configuration on the left. This is literally all you need to add to Claude Desktop's config file to connect it to GitHub. 4 lines of meaningful config. You specify the command to run, npx, the package name of the MCP server, and your GitHub token as an environment variable. Now look at what happens automatically when Claude Desktop starts up. First, Claude Desktop, acting as the host, reads that config and spawns the GitHub MCP server as a child process on your machine. Second, it creates a client inside itself and connects to that server process via stdio transport, just reading and writing to standard I/O streams. Third, the client automatically sends a tools/list request. What can you do? The GitHub server responds with a full list of available tools, their descriptions, and their input schemas. Fourth, Claude Desktop now knows about all those tools. They are part of its context. When you ask a question that requires GitHub data, the LLM can choose to call any of those tools. Look at the available tools at the bottom: create issue, list pull requests, get file contents, create branch, push files, search code. Those are all automatically available the moment the connection is established. One config file. 4 meaningful lines. Full GitHub access for your AI. And that's a wrap. Let me give you the 4 things you should walk away with from this video. 1. The 3-layer architecture. Host is the app you use. Client lives inside the host and handles the protocol. Server is where capabilities live. That's your mental model. 2. JSON-RPC 2.0 is the language of MCP. Every message between client and server is a structured JSON object with a method, an ID, and params. Clean, readable, standard. 3. Transport is separate from protocol. stdio for local servers on your machine. HTTP plus SSE for remote cloud deployments. The protocol is the same either way. 4. The end-to-end flow. User types a request, host passes it to the LLM. LLM identifies a tool call. Client sends JSON RPC to the server. Server executes and returns data. Result flows back up to the user. That's the complete picture. Thanks for watching. If you enjoyed this video, make sure to subscribe for more content like this. See you in the next one.